Okay, so welcome back everyone after the coffee break. So we continue with the next session, still on AI geomodeling, but now moving to geological survey organizations. And our first speaker is Mike Hillier, who was, how many years have you been at the Geological Survey of Canada?
Continuously since 2012.
Yeah, so quite some time.
Yeah.
And working at the survey, but finding always time to do research on geological modeling methods, and a very nice compilation now, which will be also his PhD soon. It's very exciting, and we'll be a part of this work today. So please, Mike,
Perfect.
Go ahead.
Thanks, Florian, for that introduction. So the title of my talk today, it's going to be about advancing 3D implicit geological modeling with implicit neural networks using our new neural model. It's called GeoINR. I would like to acknowledge my collaborators in this research, including Florian Wellman, of course, Eric de Kemp, Boyan Broderick, Ernst Schechler, and Corinne Berdard. I'm going to give a brief outline for the talk today. So I'm going to briefly go over our motivations for why we started getting involved with AI research. Give a brief overview of the current landscape on AI-driven methods for 3D geological modeling. I'll give some details about implicit neural representation networks and our particular neural model called GeoINR. I'll present some of our latest 3D geological modeling results. I'll show how well they can scale. I'll provide some challenges related to this research and provide some future directions and conclusions. Okay, so to start, our motivations to develop AI-driven methods for implicit 3D geological modeling is really because there's been a lot of, there's limitations, with existing implicit approaches. So implicit geological modeling is one of the most common forms of methods that can be used to produce 3D geological models. And, they have some limitations that include modeling artifacts, which Florian briefly mentioned. And these can occur in complex structural settings, as well as in different data configurations. On the bottom left-hand part of the slide here, I'm really showing some examples of what these artifacts can look like. And the point that I really want to convey here is that these models, the interpolations are mathematically valid, but when you look at the global 3D geological model, they can produce geologically unreasonable results. And so the second limitation is that they really lack the flexibility with incorporating a complex and diverse set of different constraints, and they really lack the scalability with increasing numbers of different constraints as well. And ultimately, for a 3D geological modeling system, we really want to be able to integrate and synthesize all the available data that we have, along with our knowledge, to make the most representative 3D model that's the most predictive. And I believe that AI-based methods can really have a lot of promise towards achieving those objectives. So the applications for which we want to apply our methods is to support national scale 3D geological modeling initiatives. And these are becoming much more common among geological survey organizations around the world today. To start this process at the Geological Survey of Canada, we, my colleague Eric de Kemp, he developed this priority map that you see in the top right to sort of prioritize where we give our 3D modeling efforts. And there's 3 different priority zones. So we got green, which is the top priority. We have a medium, which is an orange, and we have the red, which is a low priority. And there's different layers that go into the production of this map that include data availability, geological complexity, among some other layers. But as you'll notice, a large portion of the country in the western part of Canada is in the top priority zone. So we want to first apply our methods to develop a 3D model of the entire Western Canadian Sedimentary Basin, which I'll refer to as the WCSB. And so on the bigger map here, I'm showing the footprints in red of that Western Canadian Sedimentary Basin. And the production of this model is a part of a program, a project within a program in the Geological Survey of Canada called Critical Minerals, Geoscience and Data, or CMGD. And this model is also going to be used to contribute to the Atlas 2027 project, which is an updated version of the Atlas for this basin. And the goal is to use this model to support 3D critical mineral prospectivity downstream. And then after that, we're going to enhance the methodologies to really apply these new methods to a lot more complex structural settings, particularly in the Canadian Shield. So here's a brief overview on the landscape in AI-driven 3D structural modeling. The methods that have been proposed and have been published are very promising, of course, but they really remain in a foundational and exploratory stage of development currently. And I would like to note that the revolutionary advancements that the world has seen in the last 2 years, particularly with the LLMs and deep learning, really has yet to be leveraged within this field of research. So I think there's a tremendous amount of opportunities, and it's an exciting time to really incorporate things like transformers, how well they can scale, embracing the idea of multimodalities, as well as using the emerging idea of using agentic workflows to really support the next generation modeling capabilities in 3D modeling. And on the bottom, I am showing some commonly used architectures that are used for 3D modeling. We have the convolutional neural network on the bottom left, which is commonly incorporated into the UNet architecture. And in the middle, we have the multi-layer perceptron, or the MLP. It's a very simple network, but it's very capable. It's known as a universal function approximator. And we've also shown how graph neural networks have been used to support implicit 3D modeling on tetrahedral meshes. Meshes can be viewed as a graph. I'd like to establish the foundations for implicit geological modeling, which will be useful to understand the rest of the talk. So we really try to seek to find a mathematical representation of geological features in 3D. And to do this, we use a scalar field, 5x, where x is just the spatial coordinates, x, y, z. And for every position, we have a scalar value. And this scalar field is going to model the geometric variability of subsurface geological structures and interpolate our data points. And in implicit modeling, we have commonly 4 different data types. We have interface data, which is the circles that can be sampling horizons, unconformities, faults. And we can also have planar data, which is the bedding orientations. We can also support linear orientation to incorporate fold axis constraints. And the triangles here are geological unit observations. And there's various different kinds of mathematical methods to approximate this function. But once we have this function, we evaluate it in a volume of interest. And as you can see, the scalar field that I'm showing here, it really interpolates the subsurface geological structure. And once we have this field, we can then extract geological surfaces from that using ISO values associated to each geological interface. And so we use this ISO value in a Martin cube algorithm, which triangulates wherever that scalar field is at particular value. And with these interfaces, we can define regions and domains and geological units using these ISO values and inequality constraints. Here are some different examples of what an implicit scalar field would look like for various different geological features on the left. And on the right is the geological units that correspond to that field. And again, we use these ISO values for the particular interfaces to define these units and geological domains. So implicit neural representation networks, they're neural networks that parameterize scalar functions. And the sole objective is to really learn how we're going to map the coordinates into various representations. It's very diverse. It can do 3D geometry, images, video, and audio. And here are a bunch of different examples in the AI community for which these networks have been applied. The only one I'd like to maybe draw your attention towards a little bit is the one on the top left. So this is where these neural networks have been used to characterize the latent space of representations, in this case of chairs. And this is a very useful space to interpolate between different kinds of objects in a way that ensures that it's a geometrically valid type of chair in this case. But obviously, I think this is going to be a powerful concept in geological modeling, which I'll talk to a little bit later. So these networks, I call it, well, INR for short. They typically use multi-layer perceptrons, but they don't necessarily need to do so. You can also use a GNN to do that mapping between coordinates and scalar fields. But here they commonly use MLPs. An MLP is really comprised of three different components. We have the blue, which is the input layer. And in our examples, we are going to be using the XYZ positions of a point in 3D space. And these inputted features get transformed into abstract representations within the hidden layers of the neural network. And so during the training process, these abstract representations, they start to encode more useful meaning to be useful for predicting structural features. In the final layer of the hidden layer, these abstract representations are going to be transformed into the scalar field in the output layer. And the activation function, like any other neural network, it introduces nonlinearities, which allows the network to capture and model complex features. We commonly use ReLU activations, soft plus, as well as sign activation functions. So I'd like to introduce GeoINR. This is our customized INR network specifically designed for 3D implicit geological modeling. It's comprised of a series of stacked MLPs, and each MLP is going to be responsible for modeling a distinct geological feature. And each MLP is also going to output its own scalar field. In this particular example, what we're doing is we are modeling three distinct features. We have the folded strata, the unconformity, and the flat strata. So on the right, you see the volume of interest, and what we do is we derive a resultant scalar field, which combines all these individual scalar fields in defined geological domains in such a way that it respects the geological processes of erosion. And so we use our scattered geological observations as input into this neural network. It has unique advantages over classical implicit approaches, and namely it's really flexible with incorporating different kinds of data and knowledge constraints very easily. And we'll also demonstrate how scalable this network is. And so I want to note that each data set is trained separately. We do not train on a large ensemble of geological models yet, for which we then perform inference on an unseen data set, and we do not support faults or shear zones yet. I'd like to mention a couple important points about training these neural networks and neural networks in general. Loss functions are a very critical role during the training process. They measure the prediction error, which is outputted by the neural network, and it's really the mechanism by which we can incorporate data and knowledge constraints. So these errors during the backpropagation process propagates those errors to the different network layers, and this allows us to compute the derivative of the loss with respect to the network weights, or the gradient for short. And once we have this gradient, we can then update the weights in such a way that we will get a smaller error in subsequent training epochs. And give a hypothetical example of what a loss surface will look like. And during training, you're going to exist somewhere on this loss surface. And the whole goal is to find the bottom of this loss surface, and it's going to correspond to where we optimally fit our data. And we just, at that point, we find the negative of the gradient, and that's the direction which we optimize the weights. Key to training our neural networks is constraints on stratigraphic relationships. And these relationships characterize above, below, and on relationships. They're very important for incorporating the nature and the stratigraphic sequence of units, and as well as how erosional processes affect the spatial relationship for erosional unit. And those relationships are extracted from a stratigraphic column and then applied to our data set. And we have customized loss functions for all these constraints, utilizing an approximate sign distance as an error measure, and it essentially measures how far a point is from a reference interface. And this is our loss function that we have for GeoINR. It's the total loss or resultant loss, which is a sum of all the individual losses. And that each loss function corresponds to its own distinct data type. And in our case, we have one for interface data, unit loss, orientation, and an optional smoothing loss. And this is why it's so flexible for incorporating new kinds of data constraints or knowledge constraints by just introducing an additional loss for which we add and optimize. Moving on to an important concept in GeoINR is the idea of transfer learning. So to demonstrate why this is important, I'm showing the effect of different initializations of network weights on the starting scalar field, which you see on the left. So when we increase the network's complexity, adding more layers and more neurons, we see that the starting scalar field's complexity correspondingly also increases. So this is a very poor starting point for training when structural continuity is a very important concept in geology. So how we solve this problem is by doing a geometrical initialization. So if we were to model intrusive features, we do a spherical initialization, and if we do stratigraphic features, we pre-train on a synthetic layer cake model, and that is transfer learned to a new problem for which we will start evolving that starting scalar field from. I'd like to start highlighting some results. This is of a sedimentary basin, the WCSB, just the lower Paleozoic portion in Saskatchewan, Canada. And it's a well data set for formation top markers and informational markers. We are using 16,000 points. And I'm really trying to highlight the similarity between the results that we obtain with our method and GoCAD SCUA. And we see a very close similarity between these models. And it's a form of validation for our method. Moving on to a different example, we have a deformed metamorphic setting in central Baffin Island, Canada. It's an outcrop data set, so we have no depth information. It's using interface, informational, and orientation observations. And our purpose for validation is to produce the generalized source map in the top left and the results you see on the right. So the top right is where we just use a limited number of interface points along with informational data, and you can see the close correspondence with that source map. And when we add orientation data to it, you see a much closer match. Moving on to large scale, we do the WCSB, but this time across Saskatchewan and Manitoba provinces in Canada. And here, instead of modeling 7 formations that we saw in the first example, we're modeling 45, and this time we have a total of 6.2 million constraints, which combines data and knowledge being our stratigraphic relationships. It covers a very geographically extensive area, and because of that, we have multiple UTM zones, so we have to basically unify that into a coherent space by doing projection. Here are some preliminary results for our geological surfaces for this model. I want to point out that our model has not been fine-tuned in any way. It's been using the same model parameterization that you saw in all the prior examples. And so there are some room for improvement here, but this is what we were able to achieve out of the box without any fine-tuning. And this is the volumetric model of the basin, and the red lines show where I'm going to be showing you some cross sections. So starting with the southernmost east-west section, this is really to highlight the data fitting characteristics of the algorithm. And as we move north, you can see more so how the unconformities erode some of the older formations. And again, here's another section that really highlights these unconformities and how well it fits the data. Next, I want to move on to highlight some of the computational scalability. This is really enabled by cloud computing infrastructure. And what we do is we use distributive training techniques where we partition the data across multiple GPUs. One key point that I'd like to highlight in terms of our results is that for a 6 million constraint data set, we were able to reduce the computational time, which is estimated to be roughly 2,000 years, using traditional implicit methods, using radial basis functions, using the same type of constraints. We took that from 2,000 years to 35 minutes. So we've achieved some significant computational capacity that's really allowing us to think about what kinds of other kinds of data sets can we integrate into the process, or maybe we want to start modeling more extensive national scale models. So I believe that we have a method that has that potential. Here's a graph that just demonstrates the computational time as it scales with the number of constraints. There's two different domains here. We have below 2.5 million constraints. It's roughly constant computational time, whereas above that threshold, we get a more steeper linear relationship. I want to talk about the challenges, which is really important to talk about when we're developing AI methods for 3D structural modeling. And the very first, most important one is that we really have a real large lack of training models that are realistic and validated by experts. It's certainly encouraged that we can use synthetic models during the training process, but it's my opinion that they're just not sufficiently realistic enough yet. So I really believe that we need to have better 3D geological simulators that are not just structural, but multidisciplinary and temporal. I want temporal in there because I want to teach the AI method a lot about geological processes. Related to this, we also need methods that allow us to sample these synthetic models for observations that mirrors how real-world data is collected. Particularly what I mean here is in geosciences, data is very heterogeneously distributed, clustered, sparse, and also the interpretive nature of geological data and its associated uncertainty. I also want to make a point that these methods also require a significant amount of model parameter experimentation with model parameterization. You need to have a system of tools that allow you to analyze the effects of different model parameterizations and how they affect the modeling results, and to quickly understand it and make sense of it. And related to this, we need better metrics that allow us to measure how geologically reasonable or how geologically valid an output model is. And whenever we try to include new kinds of data and knowledge constraints, we sometimes have to design custom loss functions. I have a question as to whether or not these loss functions can be learned, because a couple of weeks ago, there was a paper entitled Dr. Eureka, where they actually used an LLM within the training loop that actually wrote the code for the reward function or loss function, which then gets optimized. So that could be a potentially exciting way of optimizing these kinds of methods. In future directions, we aim to train with a large number of diverse 3D geological models, including synthetic models. And the sole purpose of this is to characterize the latent space that we've heard of in some talks here at the conference, which is exciting to hear. And this latent space is going to be used to represent the space of structural geological models to enable the production of generative models. And it's in this space that we can interpolate between models and ensure that they're geologically reasonable or valid. And it's an effective means of interpolation. We want to include faults, and we're also experimenting with physics-informed neural networks coupled with GeoINR, with coupling seismic data into the process. To conclude, I think these networks are effective for implicit 3D modeling. Our method supports conformable stratigraphy and on-conformity features. It's flexible for all kinds of different data and knowledge. It's highly scalable, has potential for national scale modeling and processing of big data, and it's diverse in different settings across large extents and different data regimes. There are limitations. We don't have faults yet, and I believe that there's room for improvement in fitting finer details. We're going to produce a very large WCSB model across 4 provinces and 1 territory. I think it's an exciting area of research to really enable the comprehensive integration of geoscience data for improved predictive modeling. And again, like I said just before, we're going to be training on large ensembles of models and then testing the latest developments in AI, particularly using vision transformers.
When you talk about nation-scale models, I mean, realizing that many countries are a lot smaller than what you already modeled here. I think just did a quick calculation, so it's more than 3 times the size of Great Britain, what you modeled in this one.
Yeah, I think we quickly looked at it. I knew it took all the area of France and Germany and some other countries, so we're already there, but I think we have capacity for even larger.
Yeah. But open for questions. Time for questions. The audience. Some of the scaling. Yeah, please.
How many models would you want to receive in an ideal world as a training data set, rather than synthetic ones?
I would prefer they're all non-synthetic, but the reality is that there's so limited number of 3D models. So there's a big question is how many models we need to really characterize this latent space. So it's kind of an open question currently, but as many real models that we can. At the survey, we built 3D models for the last 3 decades. We're going to be using all those and then data augmenting them. So we can turn like hundreds of models into tens of thousands of models. But then, yeah, augmenting that with synthetic models, probably hundreds of thousands to millions, potentially.
Sean, you had a question?
Well, yeah, I did. So you're saying about the synthetic data where you've got like a spherical model for pre-training on and like layer-cake models for
Yes.
Yeah, but if you didn't pre-train on those and if you just had, say, like a random initialization, then would you still get a model out that looks reasonable? Or?
Yes, but once you increase the network's complexity, more and more and more, that starting point is going to be so far away that structural continuity might be lost during the training process. I found that like once you start going beyond like 5 layers, if you do different initializations, you can get very different models, right? So it's really a way of also reproducibility. And I think it's also an idea for a hybrid approach where we can pre-train on conceptual models as well.
Yeah. Awesome. Yeah.
Great work and great presentation. I was just wondering about your training database. If you're training on, say, real models, Florian made a point that a model is just a model and a hypothesis. In the end, isn't there a risk that you kind of teach your neural net what the implicit interpolation used to build these reference models is using, which is minimum Laplacian or minimum Asian or so? I mean, isn't there a risk to kind of learn what the other implicit methods are doing?
Yeah, that's why I don't want to train on models that are produced by implicit modeling methods. That's why I want so many more real models that are realistic and have been validated, and that might push for more realistic geological simulators. So we sort of can get out of this negative feedback loop where we're actually introducing problems. But yeah, it's a sort of open question. It's a new frontier. So
I don't have an answer.
Yeah.
Thanks. Great talk, Mike. You brought up the topic of topology at the very beginning, and I was wondering whether your training set is, as a lightweight version, is just topological representations that are fully realized 3D surface or volumetric models. Because I think a lot of the trouble, like Florian's talk we get into, is around topological violations in terms of geological reasonableness. Would that help, do you think, or do you still think the surface representation is an important training source?
I think it is an important source, but I believe that introducing a topological constraint into the process is something that would be very beneficial to ensure. On the very first slide, sorry, this is why I initially got into graph neural networks a few years ago, was to use it as a mechanism to introduce a topological constraint to really resolve the implicit problems of the bubble generation factory when we have really complex models. So Sam Thiele put a paper in 2016 that was about the topology of geology. And I wanted to use this because graphs is exactly this. And it actually encodes the spatial topology. And if we knew that a priori, I wanted to include that into the modeling process. In practice, though, what happened was that I could do that for a very simple data set. But when I applied it to a tetrahedral mesh containing tens of millions of nodes, many different edges, it was computationally intractable. Even by today's computers. So I love that problem. I was obsessed with that problem for too many years. I had to let go.
Thanks a lot. And thanks a lot again for the nice, great presentation here.
Thank you.